Hello, myself Umesh Kumar. Today we will know about control switching device. As we all know that we use CSD relay. Control switching device short form is CSD relay, and generally we use it in bus reactor, or we can say shunt reactor, ICT, capacitor bank, and inlines also. So today we will discuss about the basics of control switching device, what is its effect, why we use it. So let's start. Today the highlights of this webinar is the first, if anyone is watching this webinar, then first question will arise in his mind that what is control switching. So obviously our first topic is what is control switching. Next one is why it is required. Third, we will see the different applications. What is the application of control switching, and in which equipments we apply this? How many equipments get benefited with this? Fourth one is working principle of control switching, on which principle it works, how it works. After that, we will see the different features which only Vigimax Synchrotech Plus provide uh, to the customers. There are so many other relays available in market from different companies. From that, how our Vigimax Synchrotech Plus is different, we will show here. Next, we will provide a little information about what we have done. Our isosceles or scope team has achieved in installation of commissioning of Vigimax CSD relay, and how we provide the service to our customers. It may be the power grid or different utilities. In next, we will see, we will recommend some recommendations to our client for healthy performance of CSD relay. And in last, we will analyze the graphs of CSD, which may consist on controlled and controlled switching of uh, graphs. That will clear more your concept. So let's start it. First, our question is why control switching? What is control switching? Control switching is one of several terminologies applied to the principle of coordinating the instant of opening or closing of a circuit with a specific target point on an associated voltage or current waveform. कहने का मतलब है कंट्रोल्ड स्विचिंग को हम लोग कंट्रोल्ड क्यों बोलते हैं? व्हाई वी कॉल्ड इट कंट्रोल्ड? Because when we provide or when we give the command through TNC or BCU to breaker, in that condition it may not be controlled. कहने का मतलब ये है कि आप जब TNC या BCU से कमांड देते हो तो ये पॉसिबल नहीं, ये हर एक टाइम ये पॉसिबल नहीं होगा कि आपका वोल्टेज पीक पे ही करंट शुरू हो. अब ये वोल्टेज पीक का कॉन्सेप्ट कहाँ से आया? एक्चुअली हम लोग सबको ही जानते हैं कि वोल्टेज के पीक पे whenever the current will start from voltage peak, in that condition the inrush current inside the reactor or ICT core will be minimum. So due to that, this terminology also we say it point on wave switching or synchronized switching. So why synchronized? We just synchronize the command which we get after, which CSD relay get after TNC or BCU. It takes some delay and synchronize that command with voltage reference graph, which it getting from previous, that is a bus voltage So it just synchronizes the command with bus voltage, and as a result it gives the command to the breaker after some delay, and finally the breaker electrically become closed at voltage peak. So it is the main work of CSD. It just controlled the switching of breaker. Next, we will see in which equipments or what is the applications of control switching. So generally in India nowadays we have implemented our CSD relay in 4 different equipments. First one is shunt reactor or bus reactor. Generally, the switchings of bus reactor in substations is more frequent because switching is more frequent due to this its breaker or its winding conditions will be more harassed if the closing is not controlled. Controlled, I mean to say, if the breaker is not electrically closing at voltage peak, in that condition, the in closing condition, ingress current will arise, and in opening condition, arc formation will happen. That will damage the breaker contacts along with the bus reactor windings or its insulations. To prevent these effects or these things, we generally use CSD. In power transformer, at the time of re-energization, when we re-energize it, uh, some inrush current arise in ICT core that may be up to 2 to 3 pu. Pu, I mean to say, it may reach to 2 to 3 times of the full load current. Due to this inrush current at different substations, we have seen the tripping at the time of ICT first closing or re-energization. To prevent this, we use CSD relay, and with our point-on-wave switching, we have just minimized this inrush current up to 0.002 pu, which we will see in our next slide. In capacitor bank, we have also implemented our CSDs like in HBDC Bhiwadi and like in other substations also. In capacitor bank, we minimize voltage and current transient. We will see its graph also in our next slide. In transmission lines, also we have implemented our CSDs in different power grid substations. Generally, we use the CSD in transmission line to minimize over voltages. Earlierly, these over voltages were prevented with the help of PIR, as you know, pre-insertion resistance. But nowadays, Power Grid and other utilities are using CSD relay for lines also. So in next, our main question is why control switching is required. So next slide we will see it, why it is required. First, why controlled switching is required. We have to know that what is uncontrolled condition and what is its effect on our system. Then only we can understand the benefit of control switching. So, what is control switching? Control setting in control switching, depending on the reactive load being switched. Whenever reactive load being switched, different undesirable consequences can occur, such as restrike, reignitions during opening of the bus reactor, and high inrush current will arise during closing operation in bus reactor, ICT, and capacitor. Also present. What is the consequential negative effects resulting from random switching? Here, whenever we will give the command through TNC or BCU to breaker, the operation which will occur, that will be called random, because here is no any synchronization is with bus voltage. That's why we have mentioned here random switching. What is the consequential negative effects? First of all, the power quality degradation, short over voltage to industrial customers, high frequency disturbances. Transient will arise in capacitor banks due to capacitor banks closing and opening, uncontrolled closing and opening operations. Second one is remote disturbances, like it may be line faults. And next one is reduced power equipment life. It meant to say the uncontrolled switching will decrease the power equipment life. Like whenever at the time of closing, the high due to high inrush current, there may be some electromechanical stress inside the core that may hamper the insulations, winding insulations. Next one is mechanical stress, because it is electromechanical force due to the inrush current. It may uh, arise some mechanical stress on electrical windings also. Then now question will be, before CSD, what was the traditional solutions? So we have mentioned here also the traditional solutions. In light of previous problems, one or more of the following remedies have been applied to alleviate the consequences of worst case of random switching. What was these? First one is fixed series inductors, pre-insertion series inductors, pre-insertion resistors in opening operation in lines, breaker, closing resistors, and the last one was metal oxide shunt surge arresters. These were the traditional solutions which we were providing in past. But nowadays, in spite of all these, in place of all these, sorry, we use CSD. Now, we will go through some graphs. What is random opening? Here, we are watching random opening graphs. It is current graphs, and these are the digital inputs which we provide after commands from BCU or TNC. Here we can see that we have given the command here. At this point, if you can see my cursor, here we have given the command through TNC or BCU. As we know, in opening condition, breakers took some time, like 18 to 20 milliseconds. It may be up to 25 milliseconds. So whenever we will give the command through with the help of TNC or BCU, it will take the opening time, whatever uh, the breaker have. After that, it will open the breaker mechanically first. In this condition, as we know, in opening breaker, first of all, the mechanical contact become open. In open situation, circuit breakers mechanical contact become separate, and after some arcing contact become open, then only breaker become electrically open. So here we can see, uh, at this instant, before voltage zero, before current zero, because it is current graph, because before current zero, the breaker has been electrically open. This effect is the next half cycle of the current. It is showing here the reignition or re-striking inside the breaker contact. Due to this, uh, there are great bad effect in between the contacts, and also this may arise problems in our equipment's windings or reactor windings insulation. To prevent this, we will see, after using CSD relay in a series of the given command, the CSD relay which command controlled command will provide, how it will just resolve this issue. Here, if you can see my cursor, initially we have given the random open command here. After some delay, this delay you can see, it is calculated delay, calculated by relay. Uh, this calculation relay perform on basis of input, the timing input, breakers, main contact, and pre-arcing timing inputs, which we provide at the time of commissioning. On that basis, this relay took this delay. Actually, for voltage peak opening, I mean to say, at voltage peak, when current will become zero, only in that condition, no any arcing or re-striking will occur. To perform this, the CSD will calculate if we will uh, travel back from here, because it is our desired condition. Here the current should be zero. So if we will travel back, here we can say this timing, it is mechanical timing, whatever the breaker took for opening. After that, this calculated delay, CSD relay, has took for provide the controlled command. CSD relay will provide command from here after calculated delay, or we can say it synchronization delay also. Command CSD relay will out the command from here, and this command will last after some opening time, till some opening time. In closing condition, since initially in for closing we have only voltage as a reference, so here you can see the voltage graph, because as an input, we have to provide the bus voltage in CSD relay. Uh, that bus voltage which through which that equipment is going to be charged. If we have implemented the CSD relay in main bay, and through main bay, that bay is just closing with attached with bus 1. In that condition, we will provide only bus 1 voltage in CSD. So it is here the bus voltage, and CSD will synchronize the command with this bus voltage. Yeah. Uh, Again, our concept point on wave concept, according to this, the at whenever at voltage peak the current will start, only in that condition we can minimize the inverse current. Not completely, but it will minimize uh, at very good instant. So it is compulsory to start the करंट फ्रॉम वोल्टेज पीक. वोल्टेज के पीक से जब हमारा करंट शुरू होगा, उस कंडीशन में ही इंडक्स करंट को मिनिमाइज किया जा सकता है. इस चीज को सीएचडी रिले कैलकुलेट करता है. बैक ट्रेस, अगर यहाँ से हम लोग बैक ट्रेवल करें, जैसे कि आप देख पा रहे हैं, ये हमारा मैकेनिकल क्लोजिंग टाइमिंग है, जो कि ब्रेकर का क्लोजिंग टाइम, एज वी ऑल नो, breaker took some time for closing. It may be around 80 to 100 milliseconds. It may vary from breaker to breaker. So it will took that closing time, mechanical closing time. After that, it will calculate the delay. Again, as I told previous, for synchronization, here we can see, here it is synchronization from voltage rising is. Here from this instant, it has started it. It has given its command. Sorry, and it has the synchronization has been started from voltage rising is. So here the synchronization has been started, and after some delay, it has given the command to the breaker. In closing condition, the first when we give the command to the circuit breaker, the breaker become electrically closed first. I mean to say, its arcing contact become closed first, and after some time, its main contact become closed. That duration between mechanical contact closing and electrical contact closing, that duration is called pre-arcing time. In our CSD language, control switching language, we say it the pre-arcing time. So the simple formula is the main contact timing minus pre-arcing time is equal to breaker electrical closing time. That is electrical. Here it is electrical closing time. We can see here the mechanical contact is closing here at this instant, but our breaker is electrically closing here at voltage peak. This timing is planned pre-arcing time. Okay. So with CSD, we have controlled this, and as a result, the CSD has been electrically closed at voltage peak. With with the help of this, induced current has been minimized. our CSD relay is Vigimax make and Scope with collaboration of Vigimax provide CSD relay in India and Scope with the help of Isocellus and Scope we just commission Vigimax Synchrotech Plus in India and abroad also. So till now, we have commissioned up to 1,000 Vigimax relay in India in Power Grid and different utilities, state utilities. So uh, then the main question is why the customers has took the relays from us. Obviously, our relay has some features which are different from other companies' relay. The first one is our CSD relay is we can use it or we can install it in any make of circuit breaker. I mean to say we can install in it in BHEL breaker also, which is hydraulic or ABB pneumatic or Elstrom spring. In all types of breaker, it may be AIS or GIS like Huseng, Pingao. We have just implemented or installed our relays in all make of breakers. So uh, it is the main feature of our relay. Next one is Vigimax CSD is having a separate inbuilt bypass module, which became different us from other relays. ये बाईपास मॉड्यूल का जो सिस्टम है ये केवल हमारे विजमैक्स सिंक्रोटेक प्लस रिले में ही है. इस बाईपास मॉड्यूल के मदद से आप स्काडा से रिले को इन सर्विस आउट ऑफ सर्विस कर सकते हो. आपको अगर कियोस्क सिस्टम है तो वहां कियोस्क में नहीं जाना पड़ेगा. आप वहां से इन सर्विस आउट ऑफ सर्विस कर सकते हो. बीसीयू से आप देख सकते हो कि रिले इन सर्विस है आउट ऑफ सर्विस है. ये सारे फीचर्स अवेलेबल है ड्यू टू बाईपास मॉड्यूल जो कि केवल विजिमैक्स सिंक्रोटेक प्लस ही प्रोवाइड करता है सर. अच्छा, अपार्ट फ्रॉम दिस सिंक्रोटेक प्लस रिले में 2000 इवेंट से स्टोर हो सकते हैं, जो कि जैसा कि हम लोगों ने बाकी रिलेज भी देखे हैं साइटों पे, इतने इवेंट्स तो स्टोर नहीं होते हैं. इससे आपको पूरी एक हिस्ट्री मिल जाएगी कि आपका ब्रेकर किस टाइम पे आपने ऑपरेट करा और उसका क्या वेवफॉर्म था. Vigimax CSD having adaptive control feature with temperature, operating pressure, coil voltage, and ideal time compensation factor to make automatic adjustment in breaker operating time. Obviously, breaker का closing time हर एक इंस्टेंट पे तो सेम रहेगा नहीं, थोड़ा बहुत चेंजेस तो उसमें आते रहेंगे. Then, for compensate those changes, we have adaptive control feature in our relay. Because temperature, pressure, all these dimensions which we have mentioned now has their effects on breaker timing. And with breaker timing change, the command will also change because the breaker timing is the main input for CSD to calculate the delay and the all logic with the help of that it gives the command. So it is very essential feature which our Vigimax Synchrotech Plus have. Next one is Vigimax Sync CSD is having a time setting resolution of 10 microsecond to analyze the switching waveform. Only in our CSD we can show you a very fine graph of close and opening, which we will show in next slide in this webinar session. Vigimax CSD is having sample rate of 167 samples per cycle, which performs very fast operation. It can record a switching waveform up to 3 seconds. Vigimax CSD is compatible with IEC 61850 to integrate with SCADA with the help of an external card, which is optional feature.
Umesh?
Sir.
Before going ahead, Mr. Prasenjit has asked to repeat again the CV closing time. Can you go back to the earlier slide and repeat
yes,
it?
sir, yes. Only CV closing, sir? This one,
Yes.
sir?
Yeah.
Yes, sir. Yes, sir. Sir, for closing, generally our CSD relay took bus voltage as a reference, because from starting we provide it to the relay as an input. So our CSD has the feature that we can synchronize it at falling edge, rising edge, or alternate edge, depending upon the different site situation. So here we have synchronized it at voltage rising edge. Here we can see it is the instant when we have given the command with the help of TNC or BCU. Here you can see, here it is random close command. Random close means we have given it through TNC or BCU directly. The command which we are providing here with the help of TNC or BCU, this command will go in CSD relay as a command initiation. The relay will took that command as an initiation. Then only on the basis of the timing, whatever we have provided, breaker timing in a CSD relay and the pre-arcing time, on that basis, it will just decide that after voltage rising is when it should give the command to perform the closing operation at voltage peak, because it is our desired location. Here the closing breaker should be electrically closed at voltage peak. Only in that condition the inrush current will be minimized. So it will give the command after some delay from the synchronization point, which is here the voltage rising edge. Here we can see the relay has given controlled close command after some synchronization delay. It will took till this point, as we can see, the command time has been extended. But before this, the breaker will mechanically close here at this instant after its main contact timing. At this instant, our CSD relay will out the command from relay to circuit breaker. From this instant, the command will just travel, and it will travel this timing. And at this instant, it will be electrically closed. As we know, in closing condition, breaker will first become electrically closed. Then only it become mechanically closed. I mean to say, its arcing contact become closed first, and then after its main contact. Here we can see at voltage peak position, breaker has been electrically closed, and then at this instant it has been mechanically closed. This time gap or this time duration is pre-arcing time. So if we convert it in a formulatic way, or if I will discuss it in as a form of formula, then we will say that the breaker main contact timing minus pre-arcing time is breaker electrical closing time. Okay, clear? I hope it is clear now. Then we will go to the next slide. Here in India, we have installed so many CSDs in PowerGrid and other utilities. So Scope, with the help of Isocellus, has installed it, and we have installed in for sun reactor, power transformer applications, also in capacitor banks in HVDC Bhiwadi, and other substations also. And we have given the good result to the client of this. Generally in India, as I have previously elaborated, our CSD is capable to install in all makeup circuit breakers. We have installed in India our CSDs in ABB, CZL, Alstom, GE, Yusheng GIS, TBA, Taikai GIS, and all these type of breakers. We have submitted our SIGRE, our paper in SIGRE also, with a circuit breaker in Indian power system. So in now from this slide, we will analyze the graphs, the main portion of this webinar session. I know that all viewers is interested in it, will be interested in it, or so they are interested in it. So first we will see the uncontrolled graph. Then only you will understand the benefit of CSD. Here we can see it is uncontrolled switching graph for reactor. It is the opening graph. Here we can see that it is the red vertical line is our target line. But here the current should be 0. But in this graph, we can see the current half cycle has been started from here, and it has been ended here. And this half cycle's amplitude is less than the previous current amplitude, right? This half cycle is the symbol of re-strike or re-ignition in the breaker contacts. It is if we are analyzing the graph and we found this half cycle which amplitude is less than the previous current amplitude, and the current is not becoming 0 at voltage peak or target line, then we can say that it is the arc formation is going here, is is performing here. Here, with this graph, we can say the re-striking is taking place. So, with the help of CSD, we will just overcome this or nullify this. Here, it is a healthy graph which we have performed with the help of control switching device, and as you can see, it is a PGCIL Roorkee graph. Yeah. So you can see here that the opening operation has been performed, or current has become 0 at voltage peak. In previous graph, here the current has become 0 here. It is also voltage peak, but the current should be 0 at this voltage peak because the breaker has been electrically open here. Ideally, in ideal condition, the breaker should be electrically open at this point as per its breaker timing. But the current has, in this graph, the current has become 0 at this instant. To overcome or nullify this re-arcing or re-strike condition, we have implemented the CSD in fine-tuned condition, and we have get the control switching graph, and we can see here that the breaker has been open electrically at voltage peak. We can see here from this instant the synchronization has been started. In this graph, we have synchronizes it on current, 0 current. So current has been started from current falling edge. Here you can see synchronization has been started from this falling 0 point, and it took the opening time. Breaker has been mechanically opened here. You can say its predicted operating time, which the CSD has been predicted after adaptive factor here. At this instant, if you can see my cursor, breaker has been mechanically open at this instant because it is a live graph, not live, but it is a practical site graph. So you can see the predicted operating time has been ended here. That means the mechanical contact has been opened here, and arcing time has been started from here. After mechanical contact opening, arcing has been started, and after 7.5 or 7.7 millisecond, the breaker has been electrically open. It is the ideal condition of controlled switching. I hope you all has been understood. Now we will move to the next graph. Reactor switching closing condition. It is uncontrolled switching at the time of closing of bus reactors circuit breaker. Here you can see this graph which is continuously coming from previous. It is voltage curve, which we have given it as an input. But at this instant, current has been started, but it has been started from voltage 0, as you can see if you are watching my cursor. it has been started at voltage 0. Due to this so much inrush current has been obtained in this operation. You can see here it is showing a 2 pu, and you can assume then what its value would be. I think it is more than 3 pu, 3.5, around 3.5. So without CSD, this type of graphs generally come, and this is the only result of high inrush current, which is just damaging the breaker contacts and the reactor insulations. If we would not be implemented CSD here, absolutely the breaker or reactor's life would not be extended what we have get after implementation of CSD. You can see, and you will say that what the CSD has achieved in next graph. Yeah, this is our healthy graph. It is also the PGCIL Roorkee graph. We have commissioned our CSD relay at this substation in bus reactor. So it is the voltage curve, and the current has been started from this instant. Here you are watching these vertical lines. What are these, and what is its work here? क्यों ये यहाँ पे है और इसका क्या यूज है? Because we all know that in opening condition टाइमिंग का वेरिएशन होता ही है. अभी अगर प्रीवियस ऑपरेशंस में किसी ब्रेकर का टाइमिंग 80 मिलीसेकंड है, सपोज नेक्स्ट ऑपरेशन में वो 80 मिलीसेकंड ही रहेगा, इट इज नॉट सर्टेन. सो because the closing time changes in each operation, due to this band has been provided here, and as per our recommendation, if the current has starting is in this green band, as you can see here, it is good and healthy condition, or you can say ideal condition for CSD reactor closing. Okay, here you can see also synchronization has been started from voltage falling is right, and after some delay it has given the command at this instant. After traveling the breaker closing time, breaker has been electrically closed at this instant, and this is the pre-strike delay, or you can say pre-arcing time. Finally, breaker has been mechanically closed here. Here you can see the digital input of auxiliary contact of the breaker also. At this instant, the breaker has been mechanically closed. Before this, at this instant, the breaker has been electrically closed, and the synchronization has been started from voltage falling. It is very simple, and the logic is very clear here. The CSD will get the command. It has get the command here, because after this instant, the falling edge is started from this instant, or this point. So synchronization has been started from here, and after this it has traveled the closing time, and the breaker has been electrically closes here at this instant, and finally closes at here after pre-arcing time. So I hope I'm clear to all of you for breaker closing graph. If you have any doubt, please ask me in the chat box. I will answer it in last of the session. So move to the next slide. Yeah, it is the graph of the induced current in power transformer. You can see here the all three phases graph. It is the uncontrolled, you can say, condition of the power transformer, and you can see here the induced current. You all know that induced current is a decaying nature. So you can see here that it is the first peak is here, and it is decaying from here to the normal no load current value. To prevent this, we use CHD relay. And what CHD relay do, we can see in next graph. Yeah, it is the healthier graph of the power transformer closing condition. It is a controlled switching which we have performed in Power Grid Rourkela ICT, as you can see in graph here. In our graph, it is also has a facility that it can show the name in which substation this graph has been performed. This operation has been performed. Timing, bay, all these things. It is also a feature of our Synchrotech Plus relay. And with the help of this graph, we can see also the setting, but because it is a JPG format, so it is not possible here. If it would be the CSD STP format, then in that it is possible to see the setting of that graph, on which setting this operation has been taken. So here in it is a controlled switching transformer operation, power transformer operation. We can see here that there is no any inrush current. No any inrush current. Whatever the curves you are watching here, it is a no load current. Okay, and this is the chattering of the breaker contacts. In some breakers, it may present some bounces. Due to that, some chattering may occur. It is result of that chattering, but it is not the inrush current. As you have seen previous, inrush current nature is decaying nature, and it become roll out after 3 or 4 seconds. So it is the inrush current actual graph, and we have just minimized the inrush current to this instant. And I think it would be around 6 to 7 or maximum 10 ampere, that is around 0.002 pu. This result we generally achieved at our all sites in which we have implemented the CSD in ICT. So, and I have seen others companies graphs also. No one has achieved this result till now. Okay, next to the next slide. Next one is the graph of the uncontrolled switching in capacitor bank in closing condition. Here you can see, because in capacitor it just oppose the change of voltage dv by dt, as we all know. So we just close the breaker at voltage 0 point in capacitor bank. In previous we have seen, in reactor or in ICT, we have just closed it at voltage peak, because in reactor or in ICT it is the inductive circuit near about, so it opposes the change of current. That's why we just close it to the voltage peak. But in the case of capacitor band, it opposes the change of voltage. That's why we just close it to the voltage 0 position, as we have done here, but it is a little bit shifted from voltage 0 condition. That's why this transient has been arrived here, and its value, as you can see, is I think more than 2.5 or around 2.5. It is uncontrolled or untuned CSD. If CSD has been implemented, but that is not fine-tuned. Fine-tuned, I mean, the input we have provided is not correct, or has been disturbed due to some external reasons like breaker timings and all that, then in that condition the graphs will also be uncontrolled. So it is very, very important to keep the CSD fine-tuned, and for this the maintenance of CSD relays are very important. So here we have, as we have seen, the logic is same. As I have just understood you all in previous graphs, here the current has been started a little bit later from voltage 0 point, and the result is this high transient. It is around 2.5 pu. So to overcome this, after fine tuning, we have achieved this one. It is a closing graph which we have obtained at exact voltage 0 position, and this value has been very reduced. As we have seen in previous, it was more than 2 pu, around 2.5 pu. In this graph it is less than 2 pu, around 1.5. So it is the ideal condition and healthy condition of the capacitor closing operation, which we have obtained with the help of CSD relay control switching. Okay, next to the, yeah, it is the capacitor opening graph. We can see here that the current has been just terminated or become 0 here at voltage peak. The concept is like reactor, the same concept. Voltage, as voltage peak, we just we have done the current 0 here. But in closing condition, current has been started from voltage 0. Okay. Okay. Thank you all. If you have any doubt, please ask me. I will try to clear your doubts. Thank you.
The dais is open for all. If you have any queries, do ask. Mesh, can you inform more about how the CSD has been connected to the existing breaker? That what all things we need, what inputs do we require? Can you give input on that particular?
Yes, sir. Yes, sir. From graph, we will understand, sir. As we can see here, this is the final graph. Okay. In this, we have provided the voltage as an input, bus voltage, current from that base CT we have provided to the CSD relay. These are two inputs. We have given the main contact timing. Yeah. First one was the voltage input. Second one was the current input. The timing of circuit breaker. Breakers 52A contact. In breaker auxiliary contact for adaptive factor. And sensors input that due to which the timing become affected. Actually, the breaker's timing depend upon the temperature, the pressure, if a breaker is hydraulic or pneumatic. So we provide the sensors for temperature and pressure to compensate the timing which it occur due to which pressure and timing temperature change. So as an input we provide the voltage, current, main contact breaker, main contact timing, and temperature and pressure sensor, and breaker auxiliary contact for adaptive factor. All these five inputs are required for breaker for CSD to operate. Generally, we use a CSD relay in manual operation. If anyone have doubt, that what will be in protection condition. CSD is taking some delay to provide the command. So, my dear friends, I want to just inform you that CSD relay doesn't take part in protection. It only come in picture in only manual operation. When we will provide the command through TNC or BCU, only in that condition CST will come in picture, not in protection. So initially, when there was no CSD installed in circuit, the command was going directly to the breaker from TNC or BCU. But we have just break the circuit and implemented the CSD in series. Now the condition is we are giving the command through TNC or BCU. It goes to the CSD as an initiation, and after some delay, it gives the command to the circuit breaker. So we can say CSD is nothing but a smart TNC switch which gives the command as a controlled command to the circuit breaker. Am I clear, sir?
Thanks, Umesh. If you can stop your screen share and check the questions in the chat,
Yeah,
it
yes,
would be
yes,
helpful.
yes. Yeah, here one question is from Srinivasan KN. Is a provision to consider contact bounce time? Sorry. Okay, it was the latest one. I will start from earlier. Yeah. The question is from Prasenjit Kayal side. Bypass module also installed in Siemens CSD. No, my dear friend, till now, I have visited so many substations, and I have not seen that any bypass module is installed in Siemens. Those guys generally use the switch, bypass switch, to bypass the relay. No, any bypass module is there in Siemens. Is CS
There is an interesting question. If you can see this, for assessing breaker timing for close and open, what is your recommendation for CB testing kits? Say, sir, CB analyzer kit for assessing operating time accurately. So, so I think Mr. Srinivas wants to check that whether we are considering the time which is been obtained with the scope CB analyzer kit, or do we consider the timing given by the CB manufacturer along whenever it has been given to the substation. So, have you got this
uh,
point?
yeah. Actually, sir, we need the recent timing of the breaker at the time of CSD commissioning. So it will be more beneficial to test the breaker with the help of our scope Isaac Ultima kit. Uh, that provide the breaker recent timing with first close and last open timings that become more helpful for commissioning of the CST release. For from Srinivasan K sir side, for ICT, the limiting of ingress current depends on which factor of transformer and circuit breaker. Yes, sir. Uh, Actually, sir, ingress current generally depends on, sir, two factor. As you uh, might be know that ingress current first is the residual flux value, what is that is inside the core. residual flux always remain present in the ICT core. So induced current depends on the residual flux value. And second one is at which angle we are closing the circuit breaker. So on both these parameters, the induced current depends. So generally through CSD we use the delayed process, and we just give the command to the R phase, and then after some time delay we provide the closing command to the rest two phases, and we just assume it that whenever the R phase will close, after some time the residual flux will be in stable condition, then only we will close the Y and B phase. In that condition, induced current will be minimized. So it is our delayed process through which we commission the CSD relay in ICT. For reactor control switching, is the closing strategy detrimental to open strategy? Sir, in closing condition, reactor closing condition, we generally we have in that in closing, for closing we generally have voltage for reference. So for closing we took voltage as a reference, and we just close the breaker at voltage peak position. That angle is 90 to 10 150. Just we use this angle. And for opening we have two options, sir. We can synchronize the opening operation on voltage or current. So for both operations the angle will be different, but we can open at closing angle also. That will be for voltage reference, and we can open with current zero synchronization also. That angle will be 0, 120 and 60.
Shall I ask Vadivel sir to take the next question from Mr. Ramesh Kannan sir? That he has asked that in case of ICT, is it absolutely necessary to have a PT input for tertiary winding to get a proper flux mapping from the previous opening? So Vadivel sir, if you can reply to this.
Yeah, sure. Sir, actually, residual flux measurement is a beneficial thing. So we can do the switching and we can limit the induced current very much. But the only disadvantage without residual flux method is whenever a protection, because ICT switching is based on residual flux, right? So residual flux present in the transformer is depends on at which angle you have de-energized the ICT. That is the important thing. When at which angle you have de-energized, that decides the residual flux. But again, when we are closing, so we are adjusting the angle at the peak of the voltage with respect to some fine tuning. But in case of, so we know while commissioning of the ICT, we know what is the opening angle to be kept, and for closing what angle to be kept. So during commissioning we are making these angles decided. But in case the transformer is opened, means de-energized through protection, some fault has happened and it is operated, then the CSD doesn't know at which angle it is open. So next close operation you might have induced currents, because there is no control over the control switching device when the transformer is de-energized through protection. But if you are putting the PT on the tertiary or wherever side, if you are measuring the residual flux mapping, the residual flux will be measured at any time, whether it is manually operated or it is fault protection operated. So at any given condition, you can control the inrush current. The only disadvantage with not measuring the residual flux is this distinguishes them. So if you are using residual flux, whatever the conditions, you can limit the inrush current. If you are not measuring the residual flux, in case of the transformer is tripped or opened through some protection operation, the next close operation, the CSD will not have much control. That is the difference. Otherwise, it is not compulsory or mandatory. We can achieve, we can limit the inrush current without residual flux also. I think, sir, I have answered your question. If you have any other things, please let me know.
Yes, sir. Question from Manimaran Sampath, sir. In capacitive current is leading nature right in the graph. Yeah, sir. In graph, it was leading, as I can show you. You can see here that. So current is are leading, sir. It is current graph. It is voltage graph, sir.
If I think if all the questions have been answered, I request all to please fill up the feedback form. The link is there in the chat box, at the top of the chat box. And if you have any other questions, please feel free to ask them.
Ramalingam Rajashekar sir has asked that in 400 kV system, CSD is provided only in main circuit breaker. In tie circuit breaker, CSD not provided. Any problem if we switch on reactor through tie CB? Sir, if you have provided the CSD in only main bay, then the controlled command will be given to only through main bay circuit. If we will close through tie bay, it will be random or uncontrolled. So it will be uh, better to implement CSD in tie also. Sir, Srinivasan KN sir has asked that limiting value of inrush current for transformer is independent of transformer capacity vector group. Sir, generally we minimize the inrush current uh, as the CSD relay can. So till now we have achieved the value below 20 amperes. Uh, so I think it don't depend on the vector capacity vector groups. Okay, thank you.